Hi, my name is Michael Huar, and this is my virtual presentation on the chemistry of deep fried food. So, why is it important to understand what is happening to food on a molecular level when it is being cooked? If we understand what happens to food on a molecular level, we can understand what gives it the taste and texture that we experience when we eat it. This can help us to create better tasting food or to hypothesize by using science what foods will taste well together. In my presentation, we will be exploring the process of deep frying, which is when we submerge food in hot oil to cook it. So when the food is dropped into hot oil, bubbles form on the surface of the oil. This is actually not the oil boiling, rather the water boiling out of the food and creating bubbles in the oil. Water's boiling point is much lower than the boiling point of vegetable oil. So the water boils out of the food while the oil remains liquid. Here is a comparison of the boiling points of water and vegetable oil. As you can see, the boiling point of water is about half that of the boiling point of vegetable oil. So when the temperature of the oil reaches 212 degrees Fahrenheit, the water will transform from a liquid into a gas, while the vegetable oil remains liquid. So the H2O evaporates out of the food. This causes the food to dehydrate, and it forms a crispy crust on the outside of the food. Fat content and calories. The evaporated water leaves gaps in the surface of the food. So the oil molecules fill these gaps. This process is called oil uptake. The oil uptake amount is directly proportional to the amount of water that is lost. So the oil is absorbed into the food, and this is what makes the food juicy or greasy when you bite into it. The oil also increases the fat content of the food, and fat is energy, so it also increases the calories of the food. In the top right here, I have a model of a fat molecule. It's a very complex fat molecule. It is a collection of oxygens, which you can see here, bonded to strands of carbon with single covalent bonds to hydrogen on each side in a linear fashion. As you can see, there's a lot of linear carbon-hydrogen bonds. This is ingested into your body when you eat fried food and broken down into energy for the body to use. Most fat molecules look this way as a strand of carbons with two hydrogens bonded to each, although they can be configured more simply or more complexly, which affects how it is broken down in the body. Batter and breading. Why do we use them, and what do they do? So the batter gets dehydrated before the rest of the food on the inside. This allows the food on the inside of the batter to stay moist, and the batter dehydrates first. So the food inside still cooks but is left with more water. This creates juicier and less dried out inside food, causing it to taste better and less dry. Oils. Oils. It is important to choose carefully when selecting an oil to cook food in. Different oils have different lipids that react differently to heat and can influence the taste of the food. For example, fats in corn oil have weaker bonds, which cause them to break down in lower temperatures and can give the food a bad taste. It is best to choose oils with high boiling points and strong molecular bonds. Looking at the molecule diagram that I have up here in the top right, you can see that the saturated fat molecule has single bonds throughout. This causes it to break down more easily in lower temperatures. In the low temperature, when the fat breaks down, the hydrogen, carbon, and oxygen can be released into the oil and can influence the taste of the food. That's why it's important to use oils with more complex fats, like unsaturated fat, which has stronger double bonds between the carbons, so it will not break down as easily in low temperature, will maintain its shape, and not influence the taste of the food. That pretty much covers my presentation on fried foods, and here are my references. Thank you.